My name is Danfei. Thanks you all being here. The goal of my talk today is to convince you that the future of robot learning will be driven by human data, and that Project Aria Glasses is an excellent research vehicle for this problem. What motivates our work largely is that most AI systems we see today are driven by human knowledge. And at this point, a large part of human knowledge is captured by the internet. And this knowledge in turn gets downloaded, cleaned, and absorbed by these gigantic foundation model we see today. For the past few years, robotics community has rediscovered teleoperation as a powerful tool for transfer of sensory motor knowledge from human to robots. And we've seen a lot of successes in both academia and industry. A lot of really impressive demos on tasks we thought were previously impossible for robots to do. So for those of you who are not familiar with this topic, because I'm in the Vision conference, let me first explain what teleoperation is and why that's useful. Was the work Jay and I did back in 2020. When a human operates robots with a control device such as iPhone here, we capture two streams of data, what the robot sees and the corresponding action. This creates a direct mapping between perception and action in the policy model, essentially teaching the robot how to react to different situations without explicitly writing down the rules, which is very, very, very different from how people used to program robots. An important point here is that we're not just transferring abstract semantic knowledge, but rather by perceiving and acting through the robot's body, we are transferring sensory motor knowledge that's largely missing from today's internet data. But teleoperation creates a very, very tight bottleneck in a knowledge transfer pipeline. For those of you who have done teleoperation, you know that it requires pretty unnatural and intentional effort from the operator. And of course, having to bring the robot around for wherever you want to collect the data with. So that's very, very inconvenient, not scalable. And argue that it is unlikely for us to scale to the to reach the data scale of other domains like computer vision or language if we rely on teleoperation alone. So the central piece of question our work is really answers the question, how do we transfer sensory motor knowledge from human to robot at scale? And our research pitch is to instead learn from human experience data. And this data will be collected from human without no robots involved and contains sensory motor information essential for robot policy learning and can be captured without intentional efforts from the humans. And so with that, I like to basically tell you through a line of work that we've done, a subset of them, and try to convince you that these are really interesting research directions, and I'll tell you some open questions that's on top of my mind. So the first our research landmark or milestone was Ego Mimic, scaling robot learning via egocentric video. And this core project is to capture embody human data from egocentric view with wearable devices, which means that we can collect this data anywhere. And unlike third-person videos from internet, egocentric data captures how we as people perceive the world at eye level. And specifically, we use Project Aria glasses to capture these data, which we all familiar with, and these contain essential information for decision making, such as hand tracking and images and head localization. And our work is about turning these raw data streams into human data that can be treated as equals with human data, with robot data. So we want to view them as basically two embodiments on a spectrum that on one end, we have humans, and on the rest of the spectrum, we have different kinds of robots. And we achieve this by bridging sensing, action, and kinematic gaps, and develop joint policy learning architectures that can scale primarily with human data. Let's first talk about how to align embodiment viewpoints between human and robots. For embodiments, we discovered that to learn from human data, we actually need a human-like robots. And we didn't really have too much options back then, so we actually had to build our own lightweight robots, which are basic two 6-off arms. And one very important decision we made was to actually mount a Project Aria glasses on a robot so that it matched in viewpoint as an average adult. And for those of you who have worked with I mean, I'm assuming most of you work with cameras. Camera gaps are very important. Any gaps in camera lenses and exposure could create gaps in your models, downstream problems. So we actually use the exact same cameras for both human robots to bridge this gap. Among the many problems we had to deal with to learn from egocentric data, I want to highlight one very important challenge or interesting challenge, which is that our head moves and a robot's camera typically don't. When working with robots like ours, the robot's gripper movements is referenced relative to a fixed camera frame and can easily get action trajectories into in a fixed coordinate frame. But with egocentric human data, like the ones I just showed you, our head naturally moves as we work. We look around, move to different workspaces, and focus on different aspects of tasks. This means that hand positions are tracked with a relative to a moving camera frame. And we need to stabilize this reference frame to make human hands tracking data usable for robot learning. And luckily, Aria gives us really good hand device tracking via SLAM, which will be the key to our solution. So very kind of briefly, our solution is to transform future hand positions into a current camera frame. Here we show hands in a moving head frame, right? You have a camera, the Aria glasses tracking hands at different camera frames. But if you project it back through this VIO of the camera, you can actually create a very smooth hand trajectory. Looks like this. So this is basic, we got this by projecting future hand pose back to the current camera frame. So you see these smooth trajectories. With a line observation action space, we were able to design very, very simple architecture that co-trains from both human and robot data, and almost all of the network weights are shared among human robots. So we show that this architecture was able to learn a shared representation that scaled policy performance primarily with human data. So I won't go into too much details of architecture. So if you're interested, talk to me or read a paper. We tested robots on a variety of tasks, including the grocery task where a robot must pick a grocery bag with a thin handle and pack all the chips inside. And bags are slippery, so we'll also have to kind of react to these kind of mistakes. And laundry tasks for basically folding small shirts with different colors. And of course, we all need robots to do our pullover coffee. So our student trained the robots to do exactly that. I'll let the robot do that. Drinking water. Yeah, so, and then this robot's also able to react to different kind of situation like real-time planning or swapping kind of different kinds of balls, different colors. And finally, we can actually move the camera or the robot around because we train on so many diverse viewpoints from human data. It's actually pretty robust to viewpoint changes. So the main question we still want to answer is, does Egocentric scale with human data, right? What we want to kind of break from the shackle of teleoperation data to use human data. And here, the x-axis is our data, our time you spend on collecting data, either human or robot data, and the y-axis is the task performance score. And you can see that if you only train on robot teleoperation data, you have this moderate kind of scaling curve where more data, better performance. But with 1 extra hour of human data, you actually have a gigantic jump in performance. This is mainly because we can demonstrate the task really, really quickly, up to 10 times as fast as teleoperation with our hands. So, and also you don't need robots around, so you can collect data anywhere, which creates a massive advantage for scaling robots with human data, robot performance with human data. We also brought our robots outside to a variety part of campus. We didn't really collect new data on these new scenarios, but this kind of works. So one of my favorite examples on the lower right, where the student kept tossing on new chip bags to the robots. And then, I mean, it kind of does what it's supposed to do. It eventually fails, but it really shows the robustness of our policy trained from human data. Okay, so one other thing I want to highlight is that we want to go beyond egocentric vision and tabletop manipulation, which is pretty much the standard setup for robot learning today, towards looking beyond like vision, towards tactile and potentially full body motion. And one work I want to highlight is from a past project in Coral, where we try to learn from tactile data, where we directly strap a tactile sensor on the person's fingers and basically use that to collect tactile human data and use a camera to track the position of the fingers or the sensors. And we didn't use Project Aria glasses for this project specifically, but we could easily swap out these devices for tracking hands. But because Aria doesn't measure tactile, so we do have to instrument this to collect the tactile data. And we showed that we were able to actually train policies directly from these data to transfer this to robots. And one thing that we noticed here is that direct imitation learning doesn't actually work for these kind of complex tasks, so we had to do some RL fine-tuning online. But but the policy trained from human data was able to largely complete tasks. So there was a lot of somewhat quickly to fine-tune this policy to perform well on these tasks. I will show that the policy works on a variety of perturbations, such as new materials, new shapes of that peg, and new tasks like screwing things on a hole. So these are all achieved via fine-tuning the same base policy. Okay, finally, I want my personal favorite topic is to go beyond tabletop manipulation towards mobile manipulation. Many of you probably have seen this video called Mobile Aloha. It's a work called Mobile Aloha. It's very, very impressive, which is also partially responsible for driving all the craze around robotics today. But as you notice, it's painfully slow to collect this data, and you also have to kind of have the robot around. You can see the lower left side is 10x speed up video. So you don't want to do that, be the person who to collect the data with this kind of robots. On the other hand, human data is almost trivial to collect, as I explained earlier, and we naturally move around in our space to do all sorts of mobile manipulation. And one very, very important thing is that modern wearable devices capture more than just videos, right? We actually have the full body motion captured with our hands in a very accurate global coordinate system, along with the disseminated point cloud. This is specifically captured by Project Aria, which you can see that it more or less captures the full body motion of human. And we do think it's possible to learn full body manipulation from this kind of data. So the question that we want to answer in this work called Emma is really that. I'll wait for him to take the picture. Yeah, all right, is Emma, the question is, can we scale mobile manipulation with human data? This is done by our student, Lawrence Zhu. The answer is that yes, but we still need to borrow a little bit of robot data. But here, we don't actually need to move the robot around. It's just static robot data combined with massive amount of mobile human data that allows us to train mobile manipulation policies. And architecture-wise, it's actually quite simple. So it's exactly the same as we done before. Massive transformers train on all sorts of different data, including both human robots, shared weights among human robots models. And one thing that we did here was that we actually have this different decoder heads, end effector, upper body motion versus navigation heads. And we have the phase switch prediction that switches between manipulation and mobile manipulation and mobile. I would love to explain more about why this is necessary and why still learning truly full body manipulation, like moving while manipulation, is such a hard problem. I have some ongoing work on that, but I will skip the details here. And in terms of system, we just basically put a differential drive robot on the bottom of this robot, or same robot, so it's able to do the task. We also had to do some retargeting, but I'm going to ignore, glance over the details here. So does it work? We showed that it works on a few very challenging problems, such as serving breads or serving croissant here to a different table. And one very interesting task is this serving. Oh, actually, yeah, we compare with Mobile Aloha, and it was will show that our method performs better. And the typical failure cases of Mobile Aloha is that it just runs off and run into things. So clearly bad. One very interesting task we did was hand over wine glasses to a person. And this way we actually stress test the generalization of, because the person can be anywhere. So it learns to navigate the person just from the human data side of this. And because it only relies on human data for navigation part, we can actually collect data on a completely new scene and combine with the existing static robot data to train a robot to complete the same task in a completely new scene. So we don't have to really collect any more teleoperator data if your robot is able to handle this kind of varieties. And finally, we have this cool task where we want a robot to do grocery shopping. So it's able to do this kind of bi-manual manipulation and coordinated pick up this shopping bag and move the shopping bag to the other table to hand over to a person. Okay, so quantitatively, we show that for this long horizon task, if you look at the per stage success rate, mobile aloha the success rate kind of dies off later because it's the more progress towards the end, the harder the task is. But our model is able to still achieve 50% success rate for the entire task, which is quite impressive. And very exciting thing that we discovered is that with the scaling trend still holds, and I'm very confident about the scaling curve where x-axis is the amount of human data, y-axis is success rate, because we did 50 rollout per point on mobile manipulation. That was a long time. So it took us like a few days to run these experiments. So I'm very certain that this is the case. So these are the technical works, kind of glance of the technical works we've done in this area. We have a few other papers. If you're interested, check out our website. But I want to kind of talk you through some open questions that on my mind that maybe give you a flavor about kind of where the robotics community might be going next especially with learning from human data. So I grouped them into three categories: hardware systems, data algorithms, and research community. So for hardware systems, the question I want to answer, the most important question is, how do we capture human experience and context? And the claim here is that first-person video is not your sensory motor experience, is also not your decision making context. So they're all different things. Like what I mentioned before, our experience is more than just egocentric vision. Beyond the current egocentric vision devices, we're hoping to see more advanced and portable sensors for example, for tactile. And a good example is the Gen 2 device just presented that's able to capture other sensor modalities like audios and heart rate, right? But the things are obviously still lacking from the tactile side. We have tactile gloves and more recently commercializable EMG wristbands, but things are still quite in flux there. And the context for necessary for making decisions is also more than your instantaneous observation, right? So if you look at this third-person video, the reason that the chef turns around to look at different counters and get the ingredients from one counter pouring to the pot is because they remember that the fact that they prepared the ingredients a few minutes ago, and through years of training, right, they know how to adjust the heat appropriately to kind of to cook a good dish. And this is all more than just your instantaneous observation. And how we assimilate this kind of context knowledge into policy models is still very much an open question. On the side of data algorithm, it's arguable, I will argue with you, if you don't agree with me, that human embodiment is the most universal and is most scalable data sources. And the more human-like the robots are, this will make human data more useful for robot learning. And if the results I just present continue to hold at scale, it will make sense to have this kind of setup where you have massive amount of human data with small amount of embodiment specific data. But the open question really is that what roles should these data play, right? Like how do we actually use them to train these large robot policy models? And I have some speculations. So for example, there was a data pyramid picture that my friend and colleague at NVIDIA, Xu, presented a while ago, now became famous, that from human data perspective, you have a massive amount of human data as a foundation for training the policy, and you fine-tune that with robot data. But I would argue that it's as it's just as likely that we'll have this kind of inverted pyramid where the robot data is the foundation for being able to learn from human data, because you can argue that by learning through a lot of, by learning these basic capabilities like pick and place and insert, you are, only then you could actually properly make use of human data. So I'm not advocating for either picture. Both of them are equally likely to me. So we're seeing evidences for both pictures, but I do want to point these out here, and I want more exploration from both sides. And finally, I want to talk a bit about how to drive collective progress as a research community. For robot learning, we have made tremendous progress by coming together, build data sets like OpenX embodiment, Android. And for egocentric data, we have prior successes from Ego 4D, App Kitchen, and more recently, Ego Dex, that's more focused on the manipulation data. But if we had to learn anything from past few years of robot learning, data-driven robotics, is that large data set alone is not, won't solve the problem. We need a continuous cycle of data to algorithms to evaluation, especially on robot evaluation, which helpfully tells us what data is more useful so that we can collect more of that. At the same time, there's a unique opportunity here to build a community in that we can at least agree on a single embodiment as a data source. So along with a few academic groups and industrial partners, we're currently developing some standard infrastructure for this whole cycle. And the hope is that this would potentially enable the community to make things more comparable and accumulate more and more insights and useful data along the way. And I'm hoping to be able to share that in the next few months, so stay tuned. And with that, I'd like to conclude talk, and here's the works I mentioned. Here's the main contributor for these works, and here are my sponsors. And thank you.